Firstly, thank you for the opportunity to present our work. I'm going to try to go quickly with apologies. At 6 p.m. your time, I have to teach, so I'm a bit constrained. But nevertheless, I'm very excited to introduce to you the things we've been doing, and I hope at the very end to try to make some connection to the main theme of this workshop to some degree. So the first statement quickly is to say that in a short period of time, we've collaborated and bothered an enormous number of people. And so I'd like to, without reading out the names, thank people in our own group, colleagues at Stanford, and strong collaborations in electron microscopy and electron energy loss spectroscopy, X-ray scattering and spectroscopy and theory. And I'll try to highlight both the authorship of the relevant work and the young people who led it as we go along in the discussion. So the motivation and the thinking is actually quite straightforward, which is that almost immediately after the discovery of cuprate superconductivity, my understanding is that there were people in the community asking by analogy what other material systems might also be found. As you know, this famous result of Bednorz and Mueller launched arguably one of the largest sustained condensed matter physics efforts in the modern era, and it is still a prominent problem today. It's quite a complex one. I take here two pictures from a recent review article on this field, and I would like to just remind those who might be slightly less familiar that the generic motif of the system is that you start with an antiferromagnetic insulator, a correlation-driven Mott insulator. And if you dope generally holes, but in some cases electrons into the system, you observe a dome of superconductivity. And as you can see, even at the level of a review article, this is an enormously rich and complex phase diagram with many interesting aspects of competing instabilities, for example, that are either competing or intertwined with superconductivity. Now, in terms of the hundreds of materials in this cuprate family, they all share the common motif of being constructed by CuO2 planes. So these are the relevant two-dimensional planes that host the relevant electronic and magnetic degrees of freedom, and various stackings and spacings between them. Again, many different varieties. And the electronic states generally near the chemical potential are derived from copper 3D orbitals hybridized with the oxygen 2p like orbitals. Okay, so we'll come back to this point in a little bit. So as I said, the question is a very naive and simple one, which is, could you make in general other materials that mimic, depending on your perspective, what you believe are the key ingredients relevant for unconventional superconductivity? And in the interest of time, I won't give a broad introduction, but simply to say we've been looking at the infinite layer Nickelates. And the specific question here is, can I make something that is, say, a rare earth 3 plus nickel 1 plus O2 look like the infinite layer cuprates? This is not an original question. As I said, I believe it was lingering already in the community. The first two statements specific to thinking about this system are coming from these two papers here. These are both electronic structure calculations exploring this potential analogy. On the one hand, the analogy is quite close in that you would normally have 90 electrons per nickel. And then you could imagine if you doped holes in the system, it might behave similarly. As pointed out first by Warren Pickett and his collaborators, that actually the electronic structure does have some qualitative differences. Namely, if you look at the LDA band structure, you have these large hole pockets that are very much the same or reminiscent of what you see in the cuprates, but you have additionally small electron pockets, ones hidden in the zone center here, that are largely derived from hybridization with the rare earth 5D states. And in fact, this creates a rather interesting situation that in some language, you could say even the undoped quote unquote parent compound has some self-doping effect because of these two relevant bands that are parent, at least in the LDA limit. Now, if you noticed, if you're chemistry oriented, you can notice that we're talking about a very unusual oxidation state of nickel. And in fact, there is, as far as I know, no thermodynamic kind of a stable way to synthesize this phase. But actually, over the last few decades, there's been extremely clever chemistries developed that I'll summarize here. Namely, what you can grow readily, reasonably readily, this already requires high pressure oxygen synthesis, is you can grow the perovskite form of the nickelate. And you can do a sequence of deintercalation, oxygen deintercalation reactions. In this case, you can imagine rows of oxygen being poked out here to make the so-called brown millerite phase. And now you've gone from nickel 3+ anomaly to 2+. And if you take out the other row, then you're now in an exact structural analogy to the infinite layer cuprates. And indeed, this would be anomaly nickel 1+. Okay. So this sequence of reactions was first reported in 1983 using hydrogen gas of reducing powders. Many experiments in this field, but to take these three highlights, the next critical step, certainly that we're utilizing, is this work that found that the stability and reproducibility of this reduction reaction could be greatly enhanced by using metal hydrides. We'll be using calcium hydride. And finally, about a decade after that, so about 11 years ago, it was first reported that you could actually perform the same reduction reactions in thin film form. And we'll certainly be utilizing these three key steps in the work that I'll show you. Okay, so the first statement is, again, in the interest of time, we failed or we struggled for about 3.5 years. Given these prior works, we could grow the undoped compound, but we really had a hard time doping them. And the final thing is, I'll just go to what worked. Was trying we had focused our energies on first synthesizing the infinite layer phase and then trying to dope that system. And the idea was naively then, rather than that, let's try to do substitutional chemistry in the perovskite phase. And then if it survives this reduction reaction and the carriers are active in some sense, then that might be the right approach. And just as a personal anecdote, it's kind of funny. I was a summer student bouncing around Bell Labs. And so this was some 24 odd years ago. And this was precisely playing with doping the perovskite phase. So here's the metal insulator transition that's quite famous in this perovskite nickelate. This is neodymium nickelate. And this was an early stage attempt to do electron and hole doping of this system. And it's ironic that this is actually very close to the starting composition we're playing with. In any case, if I show you kind of the first hints that something interesting is going on, you can see here, I should emphasize this is not a zero resistance scale. And yet this is the first hint we had seen of something like a superconducting transition where we had nominally tried to do an analogy to substitutional doping in the cuprates, namely with the idea here of 20% hole doping of this system. Now, it turned out that there was still quite a bit of work to do to give you a rough hint of what you were seeing in that partial transition. And let me summarize a rather interesting materials challenge is to go back to this point that nickel wants to be most stably 2+. 3+ is a secondary oxidation state. What we want to do is very, in some sense, perverse from a chemistry point of view. We want to take, say, doped versions of this, so very high formal oxidation states, far from stability. Then we want to reduce it to a very unusually low oxidation state. And we want to, as I'll show you, use epitaxial stabilization in thin film form. And this is despite the fact that the lattice parameters between these different versions are changing by quite a few percent. And so just to visualize this challenge, those early partial transition samples look something like this. 95% of the volume of the film was decomposition products, secondary phases, or a mess. And we believe that partial superconducting transition was this first few nanometers at the interface. So by some work, we were able to expand the stability region of this infinite layer structure. And here we could achieve kind of complete zero transitions in transport. And again, to summarize briefly, quite a bit of work. You can find the details in this paper here if you're interested. Um, this and previous work in the field had shown that there's a stabilizing proximity effect, that near the substrate interface of a host that does not undergo this deintercalation transition, you can stabilize this crystal structure. So simply speaking, the best thing we thought we could do is to do this on both sides. And so we grow a perovskite heterostructure. We stabilize essentially this nickelate in perovskite form in between, and then do a deintercalation reaction out of the sides. And this is kind of a representative, quote unquote, best current sample. So on the one hand, we're very pleased that it is rather basically a single crystalline thin film. On the other hand, it should also be seen that there is quite a bit of extended defects. You might see this rectangular shift here and there if you look carefully. And so for everything I show you subsequently, this is the picture you should have in mind. Reasonably crystalline single crystal film, but with a high density of extended defects. Okay. So let's look then at the first basic results in our work here. So I'm going to show you here the perovskite resistivity function at temperature for the undoped neodymium nickelate. Again, you see this famous and striking first order metal insulator transition. This is associated with a D7 electronic configuration. And similar to that old work that I had hinted at before, if we do nominal hole doping in the system, we rapidly suppress this. And in fact, we have something that looks effectively metallic all the way down. Now, if we then perform this deintercalation reaction, again, in this kind of thin film heterostructure sandwich, we find something rather interesting. The undoped case, now neodymium nickel O2, doesn't seem to be a particularly good metal or an insulator. I'll come back to this point in a little bit. But namely, it has this kind of weak insulating upturn at low temperatures. And a number of early observers in the field has suggested this might have something to do with a condo-like instability. Now, if we take the doped version of this and now in the infinite layer structure, we see something that if I did label looks quite reminiscent to the cuprate community. Okay? And of course, the superconducting transition. So in terms of the basic superconducting properties, you see a nice kind of critical current density. In those early days, this was about, maybe we're now often seeing double this, so something approaching 0.4 mega amps per centimeter squared. Early experiments on using a perpendicular magnetic field to suppress superconductivity in the critical regime allows you to estimate a Ginzburg-Landau coherence length of about 3 to 4 nanometers typically. And finally, I show you kind of split coil mutual inductance measurements. And this is now picking up the onset of screening. And there's still a lot to be thought about in terms of how to properly analyze and think about this problem. But let me say in broad strokes that independent of the details, the London penetration depth will be of order microns, so quite long. And this is, of course, the work of Denver Lee, who I should just say is just starting his faculty position at the City University of Hong Kong last week, I think. So let me just try to give you a couple central questions. This is a very early stage of the field. And the first simple one is, it seems to have worked, then to what degree is anything different? Maybe 9d electrons in nickel is the same as that in copper. It turns out that actually there are interesting qualitative differences, and a lot of that has to do, simply speaking, with the fact that we're 1 over on the periodic table, 1 less oxidation state, and thus the orbital alignments are rather different from what is familiar in the cuprates. Now, in that system, just to give you a schematic, the kind of the electronic structure landscape looks something like an oxygen 2p derived band, an upper and lower Hubbard band derived from the the Coulomb repulsion-driven gapping. And then if you start to dope holes in the system, an early and important notion was the fact that because of this kind of landscape, what you form is actually something known as the Zhang-Rai singlet, namely that the hole that you dope in there is not really removing that last unpaired electron so much as it is taking out an electron from an oxygen 2p-like derived state, and then making an overall singlet. This is a natural basis to think about a lot of the important features, for example, the strong connection to antiferromagnetic fluctuations that seems to be prevalent in the cuprates, even in the dope system. Now, in the Nickelates, the features are similar, but the landscape is different. And namely, now we have an upper and lower, let's say, nickel 3D Hubbard band. But this is in the midst of the extended kind of 5D-like states of the lanthanum or rare earth site. And if you hold up the system to leading order, the physical picture we initially have is that you have a state that is largely derived from nickel and these kind of 3D and 5D states. Now, of course, you still have quantum mechanical hybridization. And so Tom Devereaux and his colleagues in this work, looking at that electronic structure, just to give you kind of this real space kind of projection, indeed, you still have something like this configuration, but it's much smaller in relative importance. And in conjunction with that 2D cuprate-like state, you have something that can be projected into a z-squared-like orbital derived band. And this is much more three-dimensional. And in fact, these early discussions led us and others to think about this being a potential interesting analogy to the Kondo lattice problem, in that rather than a 4F level, you may have essentially this narrow upper Hubbard band in the midst of a more dispersing 5D band. Now, to give some aspects of the experimental evidence for these sorts of things, let me just focus here on the X-ray absorption spectra. And the key consequence of this notion of a Zhang-Rai singlet, for example, is to see spectroscopically this hybridization pre-peak in the oxygen K edge. And what you see here is, for example, if we look at nickel oxide, nickel 2+, or nickel 3+ in the perovskite, you do see this prominent pre-peak. But in the infinite layer case, you see almost nothing. This is for lanthanum, and this is for neodymium. So complementary with these XAS type experiments using essentially an electron energy loss process probe, you can see the same features. This is now work done by Barrett Goodge at Cornell. So for the more specialists in the audience, then our nominal assignment would be that we're closer, or we can label this to be in the Mott-Hubbard regime, which is a bit unusual given how far to the right we are on the periodic table. Now, in terms of the phase diagram, let me say that you can, of course, dope this phase diagram, and we see a dome of superconductivity. Here I compare it with the 214 cuprates, and so it's qualitatively similar, a bit narrower. But what is rather surprising, as I said, in our results is that on either side of the superconducting dome, we have these weak resistive upturns. This is quite in contrast to the bounds of superconductivity in the cuprate, going to a good Mott insulator and to a reasonably good Fermi liquid metal on either side. And if I take, for example, another picture of this variation, nominally using the low temperature just above TC resistivity as a scale, here it also gives you this scatter I show you because of these extended defects sample to sample. But nevertheless, the trend is clear. There's a minimum associated with this region of superconductivity. I'm getting a bunch of messages. I wonder if I'm doing something wrong. Let me just confirm. Okay, sorry. The other thing I wanted to mention, just at a very preliminary kind of notional sense, is that if you plot the quantum of resistance per nickel O2 plane, this is this gray dashed line here. And so what we find is actually superconductivity is right in the regime where you can start to just dip under this scale, where the notions of band-like states and coherent transport might become relevant. Now, a quick word to say that, of course, it's very important, and it's lovely to find that other groups are also working on this problem and reproducing it. The first published example I can show you here was from the group of Ariando in Singapore. And skipping the details, actually, given how messy the materials are, I was quite surprised and impressed that in both of our data, the qualitative, indeed, many of the quantitative features are quite close. They again see this dome-like structure. So let me try to now finally squeeze in a few slides attempting to connect to the larger themes of this conference as far as I understand them. And of course, it's a central question for us, motivated in some sense from the onset by an analogy to the cuprates. Of course, a famous aspect of this problem is that the proximity of superconductivity to antiferromagnetism is a central feature that people have been thinking about. And the importance of spin fluctuations for the superconducting state is in some case broadly undeniable, and there's of course a lot of questions about how in detail that manifests. Now, it's interesting that we're stuck with a materials constraint where we can only have nice crystalline films down or up to about 100 angstroms. And we are reliant on these remarkable developments in the last 10, 20 years in using resonant inelastic X-ray scattering to be able to access and probe magnetic excitations despite this terribly confined geometry. And in a word, this is an X-ray in, X-ray out process on a resonant transition by which you can, among other things, access scattering by collective bosonic modes of the system. And so we're, of course, interested in the magnons here. And the starting point I should emphasize is that while there has been limited investigation, the prior studies of bulk powder samples in the undoped Nickelates showed no evidence for magnetic order down to fairly low temperatures. So in fact, our starting thinking was there may be no magnetic or much reduced magnetic instabilities in the system. But of course, doing the experiment is always revealing and quite surprising, at least for me, despite our attempts to look for this, is that we do see evidence for strong magnetic excitations, and this is a spectra for the undoped neodymium nickel O2. So this is a kind of a Rix intensity map and plotting out what looks very much like a spin wave dispersion associated with a spin 1/2 antiferromagnetic lattice. It's fairly broad beyond experimental resolution limit. And let me briefly then put this in comparison to the cuprates. So if I take that data, here are the peak positions and a measure of half line width approximately. You can see that we can reasonably represent the data by a simple, nearest and next nearest neighbor spin Hamiltonian. If I take a measure of the magnon bandwidth, it's something like 200 millielectron volts. And this compares with, let's say, for cuprates, typically this is about 300 to 400 MeV. The other key feature I should emphasize is that whereas the cuprate undoped cases are generally instrument resolution limited, we're here above that. And so the bound we can say is the line width of this, say, paramagnon excitation is something like at least 4.5 times larger than the cuprate. And actually, if we dope the system, this rapidly grows to be very difficult to measure that line width. But nevertheless, it's a striking situation that there is this kind of underlying or proximate antiferromagnetic instability. And it's an open question right now how we should think about this material. And so let me close you there by saying, hopefully I've introduced to you some of the basic materials and superconducting dome properties. The big question still for us is, what is the proximate instability, if that's the right paradigm, for our superconducting dome? I tried to briefly mention there's a normal state distinction. And I think the key thing to state to the general audience is that this picture that's been well developed of the cuprates, where you have the relevant CuO2 planes and this charge reservoir layer that is fairly benign in other aspects electronically. A qualitatively different aspect here is that this hybridizes to form a relevant band. And so this is actually a kind of a different system, and possibly combines aspects of kind of Mott physics of cuprates with things reminiscent of heavy fermions and intermetallics. In any case, there's much yet to be developed in our understanding of this system, but let me close there, and thank you all for your time.